Whoops. All right. Hello, everyone. Welcome. Oh, okay. Well, not everyone. So, this is, again, a bonus lecture, the last bonus lecture. I know I said I'd do it, and I am following up with my word, and we're doing it. It might be 3 weeks or so since school has been out, but you know what? We're doing it, okay? Special relativity bonus lecture, some real high level stuff, all right? So this is very non-intuitive, very weird, but also very exciting. So without further ado, let's get into it, okay? So today we're going to be talking about Einstein's theory of special relativity. Great stuff, very interesting, but very, very hard to sort of process. But let's get into it. So before we talk about special relativity, first we're going to talk about reference frames. All right. So, this is more of a everyday relativity rather than special relativity. So, let's say you have a car. You're traveling in a car at 30 meters per second. Okay. Now, to an observer at rest, you are traveling 30 meters per second relative to observer at rest. All right? Yeah. And this observer right here on the side of the road that's not moving, v is equal to 0 meters per second. They are sitting at rest relative to Earth. Okay? Still pretty simple so far. All right, now now, let's say you are in this car, right, and you're traveling with it. Now, you are traveling at a speed of 0 meters per second relative to the car, right? The car is moving. You are moving at that same velocity. Okay, you are traveling with the car. There's no difference in those velocities. So if the car was somehow sentient, right? Let's say the car was somehow sentient, it would say that no, you are not moving. Because from the car's perspective, you are traveling with it. So you actually have a velocity of 0 meters per second relative to that car. Now, this observer on the side of the road, to you, they are traveling at 30 meters per second this way, towards you, relative to you, the moving observer. Now, so this is what's known, or I don't know if it's a portion of what's known as Galilean or Newtonian relativity. It's basically just saying that motion motion is subjective. All right. So to you, this person is moving towards you, and you are at rest. But to this guy, the observer says that you are moving, and he is at rest. Okay, so again, it's relative and it's subjective. So it's based on which frame of reference you're looking at it. Okay, still with me? Okay, now, so this is basically to show you that movement is subjective. It all depends on your frame of reference, okay? The reason why is because we say that, you're probably sitting down watching this, right? We say that you are moving at rest, or you're at rest, okay? That's not necessarily true because, for one, you are on the Earth, spinning around. That Earth is revolving around the sun in the solar system. That solar system is traveling around the Milky Way galaxy. That galaxy is moving outwards in the universe. Okay, so you're not, if you're sitting there, you're actually not at rest because it all depends on your frame of reference. Okay, and this is to show you that there is no one true reference frame. There's no one correct way to look at things. Sort of like, politics, right? Everyone has their own perspective. Everyone has their own background, right? So there's no one can be completely objective. Same in physics, right? There is no one true reference frame. All motion is subjective. Okay. Now, let's get to two truths that we need to sort of believe, right, so that we can get to Einstein's theory of relativity. The two truths are that, one, the speed of light, c, is equal to 3 times 10 to the 8th meters per second, is the speed limit of the universe, right? Nothing can go faster than the speed of light. This must be true in all reference frames, okay? So if you are, whether you are at rest on Earth or whether you are rotating around, whether you are revolving around the sun, around the Milky Way, or across the galaxy, in all of these reference frames, light is traveling that same speed. Now, the same isn't true in our last example right here. Right here. Right? In different reference frames, you are moving at different speeds. To the observer, you're moving at 30 meters per second. To you and to the car, you're moving at 0. However, if it's light is always going to be moving at 3 times 10 to the 8th meters per second. No matter if it's the person at rest viewing light or whether it's the person in the car viewing light. Okay. So, and again, that's very non-intuitive, but that is true, at least from what we know, right? I mean, the theory of relativity backs that up, and it's been, proven through experiments. So it's what we know to be true, but again, science is tentative. Okay, so this brings up three different, in my opinion, really interesting new phenomena that I'd like to talk about. Now, there's a lot more with special relativity, and there's even more when you get into general relativity, okay? But I'm just starting with the basics. So there's 3 different things that are messed up because of this one rule. Oh, sorry, the second truth. The second truth that we need to know is that speed or velocity is equal to change in distance over change in time, right? But we already know that. So, first thing is simultaneity, right? If we say something is simultaneous, things are happening at the same time, right? So for this one, what we have is a train car moving along at a certain velocity. And we have an observer inside of the train car, in the very middle of it, and an observer to the outside, moving right at rest relative to the Earth. Now, actually, let's say that for now, this person is not moving. They're just in a train car, all right? And so what happens is that 2 lightning strikes happen on either side of the train car at the exact same time. Okay? Now, as the lightning strikes, it's going to let out a light wave. right? So that light wave is going to travel out in all directions. So it's sort of like a spherical wave traveling out in all directions. And eventually, that light wave is going to reach the observer, like so. And then they'll be able to see the lightning strike. And it'll also reach this observer right here, too, on the side, right? And both of these observers would agree that these two lightning strikes happened at the same time, because light from either lightning strike reached them at the same time. Okay. Now, second scenario. This train car is now moving along at a high velocity. And this observer on the ground is moving at a velocity of 0. Relative to the Earth. Okay, so now, what's going to happen is that since this observer in the train car is moving this way towards the right lightning strike, that light is going to hit him first, right? So if, right, lightning strikes, sends out a light wave, obviously, this one on the right's going to reach this observer first. Okay, which is kind of what we would expect, because that would be the same with sound too. Okay, and again, because this person is just sitting with a velocity of 0 relative to the Earth, both of those light waves are going to reach him at the same time. He's going to say that those lightning strikes happened at the same time. Really, he should be like, I don't know, here-ish, right, where the two light waves intersect. There we go. Okay, now, this observer in the train is going to disagree. He's going to say, no, I observed that this lightning bolt struck first because the light got to him first, which is again what we would expect. Okay, but here's the thing. Okay, so if it were sound, or really anything, as he is traveling towards the lightning bolt, and the light from the lightning bolt is traveling towards him, if it were, let's say we're talking about sound, and this is a sound wave instead, right? The sound from the thunder, which would be coming from the sky, or actually no, it would be coming from here. The sound from the thunder and him would move towards each other. So from the moving observer's perspective, it would be going faster than the speed of sound. Okay, but if we take into account the fact that it's a light wave moving towards him, that means that this light wave would be moving towards him faster than this light wave would. But we know that because of the laws of physics, that's not true, okay? If we go back to our first truth, right, this light wave cannot be moving faster than this light wave, okay? Because again, the speed of light is the speed limit of the universe. So it's not that the person in the train car's perspective, he would say that this one struck before that, right? But it's not an illusion. In this person's perspective, the lightning strike had to strike first than the other one. It actually struck first for him rather than the observer at rest, okay? Because if it didn't, that would violate our first truth, the speed of light. So yeah, this is when it starts getting a little crazy, okay? So again, for this observer to see something, he has to have the light weight travel towards him. Now, again, because this person is moving, and because the speed of light has to stay constant, the speed of light has to stay the same whether he's moving towards the lightning strike or moving away from the lightning strike. So for him to observe that lightning strike first, it actually had to happen first. But for the observer on the ground, they did happen at the same time, right? So this is what simultaneity means. For the observer on the ground, these lightning strikes happen simultaneously. But with the observer inside the train car, they did not. This one struck first. Okay. Now again, this isn't an illusion because again, motion is relative. It's subjective. So this shows one thing. Oops. Okay. Faster you go, the greater time between events. And again, both of these frames of reference, the at-rest person and the person in the train car, are both valid observations. They're both true at the same time. It all depends on your perspective, okay? And I know this is weirding you out a bit, and it's probably very challenging, and you don't want to think during summer break. Don't worry, I don't either. It took me a while to make this. But the next one's going to be a little easier. It's going to have more math, but it's going to be, I think, a little bit easier to understand. So hang on in there. Okay. Sorry for going fast, though, but this is a no-nonsense lecture. All right. So, next thing, time dilation. This is my favorite one because I think this is it's still not intuitive, but I think it's the best visualization. Okay, so what we have is a person in a train car, and in this train car, they have set up a little laser that's going to shoot light to the ceiling of the train car. On that ceiling, there's going to be a mirror, which will then reflect the light back down. Okay. The light is just going to go up, reflect off, go back down. And it will travel a distance of 2d, where d is just the height from the laser to the top of the train car. Okay. So, we're going to have two observers. We're going to have the observer moving with the train car, like so. And then we're going to have an observer, again, that is at rest relative to the Earth. V is equal to 0 meters per second. Okay, now, both of them have a stopwatch in their hands. Or they should. Let's get one in there. Both of them have a stopwatch in their hands. And let's say that they have superhuman reaction time. And they're going to time how long it takes for the light to go from the laser to the ceiling and back to the laser. Okay. So the time that the person in the train car records is going to be delta TP, or the proper time, and the person on the ground with a velocity of 0 is going to record delta T, which is just time. So there's going to be time and proper time. So the train car is moving to the right with a certain velocity. Now, to the person in the train car, light is just going to go up and back down. It's going to travel a distance of 2d over proper time. Okay, so we're going to say that the speed of light, c, is going to be equal to 2d over delta t p. Boom. All right, now, However, for the observer on the outside, at rest, relative to the Earth, that light travels